I want to start my lesson on absolute versus conditional convergence by asking a question. And the question is, which is more likely to converge? A series that has both positive and negative terms, or a series that has exclusively positive terms? Well, pause the video and think about that for a second. Well, hopefully it makes sense to you that a series that has both positive and negative terms is more likely to converge just because there's a higher potential that the negative terms help the sum stay small enough to converge. Whereas if you have exclusively positive terms, the chance there has to be certain conditions for those terms to decrease to the point that we approach a finite sum. And maybe the best example of this would be something like the following series here. So let's take a look at these two series, for example. Well, let's look at the first one here. Well, what's going on with this series? And hopefully by now we recognize that this series here should converge by the alternating series test. So I'll just write that. It's going to converge by the alternating series test. Again, we notice that the limit as n approaches infinity of 1 over n, that's equal to 0. And a plus n plus 1 is less than a sub n, right? A sub n plus 1 is less than a sub n. In other words, that's a fancy way of saying that the terms are getting smaller. So this series converges by the alternating series test. However, look at the absolute value of that same series. In other words, let's look at the series if we were to take an absolute value to this. So if I were to take the absolute value of this series so that I'm only looking at the positive terms that are created by the series, well, what do we notice here? We see that this series is actually divergent because it's a harmonic series, right? You can look at watch my previous videos where I discussed the harmonic series and why this is divergent, but this is a divergent series. Well, or you can also use the p-series test as well if you want to indicate that p is equal to 1, right? So let's take a step back. So we notice that the original series that we have here is convergent by the alternating series test. However, the absolute value of this series is divergent because it's a harmonic series. And what we call this type of situation here is we would say the following. We would say that our series, that what we have highlighted here, okay, this series is what we call conditionally convergent, or it converges conditionally. Okay, I'll just write that, converges conditionally. And what that means is that it converges in its original state, however, it diverges in its absolute value state, right? When we take the absolute value of those terms. Now, I know what some of you are thinking right now. You're asking yourself, wait, converging conditionally, right? Mr. No, why are you doing this to us? Why are we discussing even this level of conditional convergence versus just what we previously knew about converging? Because I was struggling enough as it was thinking about thinking about convergence in general and all these convergence tests. And now I've got to think about an extra level of nuance. Well, I'm here to kind of ease your concerns. I'm here to tell you that there is a very strategic value to being able to discuss conditional convergence. And to kind of convince you of this, I want to discuss a series that converges in its original state, but also converges in its absolute value state. And to kind of go back to our notes that we have here, a series that converges with its absolute value, we call that absolutely convergent. A series that converges in its original state and converges in its absolute value state is called absolutely convergent. Now, the reason why that is so helpful for us to discuss absolute convergence versus just conditional convergence, what's really nice about absolute convergence is that if a series converges absolutely, any series that converges absolutely also converges in its original state. So there's a huge benefit to this because sometimes we will look at series that we can't actually determine very easily whether or not that series converges. It's kind of unclear to us. But by taking the absolute value of that series, oftentimes we get a series that's actually easier to determine its convergence for. And then if we know that, hey, if this series converges in its absolute value state, then it must converge in its original state. And a great example of this is the following example that I have here. So let's take a look at the convergence of cosine of n over n squared. Now, pause the video and think to yourself, well, what test would I want to apply here? Which would be a relevant test for us to use? And if you've been racking your brains a little bit, you'll see that none really um, jump out at you, at least, or they shouldn't. The alternating series test unfortunately doesn't apply here because although this series does contain positive and negative values, cosine does oscillate between positive and negative values, it doesn't do so in an alternating manner. In other words, every subsequent term does not change signs. So the alternating series test does not apply here. So at first glance, this might be a little challenging for us, but we then ask ourselves, okay, well, what about the absolute value of this series? What if I take the absolute value of this series here? Well, what does that look like? Well, this would be the following. N is equal to 1, upper index is infinity. We have the absolute value of cosine n over n squared. Well, let's take a look at that. Now that we look at this, and now that we know that our cosine values in the numerator are going to be exclusively positive or 0, we ask ourselves, well, could we compare this to another series? And reference my 8.4 video where I talk about the two different comparison tests, but hopefully you should see right away, I should be able to compare this to the following series, 1 over n squared. I can compare these two. Well, what's going on with this series 1 over n squared? Well, 1 over n squared, this series converges by the p-series test. We can say that since p is equal to 2, which is greater than 1, this particular helper series is going to converge by the p-series test. Now let's ask ourselves, okay, which comparison test makes the most sense? Can we do a direct comparison here? Well, think about it. Let's look at our helper series compared to our original series. Which is larger? Well, our numerator is always going to be a constant of 1, whereas in our original absolute value series, that numerator is going to oscillate between values of 0 and 1. So the sum of this series is going to be less than our helper series. So we've been able to identify that our helper series is a larger series, and that larger series converges. If my larger series converges, that means my absolute value series must also converge by the direct comparison test. So we can now say that this series converges by the direct comparison test. Well, that is huge for us because now if we know that the absolute value of our series converges, then we can say the following. Therefore, our original series, cosine of n over n squared, converges absolutely. Absolutely. I can't spell. Absolutely. And so if our series converges absolutely, it converges in its original state. Okay? So that's the main strategic benefit of discussing absolute convergence. There are going to be a couple of problems that we're going to do right now where you don't technically have to really look at whether or not a series converges absolutely. If a series already has exclusively positive terms and you find out that that series converges, then you can say by default it converges absolutely. And if all I ask you is to find the convergence of a series, for example, with number 1, we can just use the tried and true test that we're used to working with to determine its convergence. But I think it is worthwhile for us to discuss, okay, even if we know right away whether or not a series converges, does it converge conditionally or absolutely? So I want to do a few more examples with you. So let's take a look at a few of these problems. We're going to look at absolute or conditional convergence. Again, if your series has just positive terms, you don't have to worry about it possibly having conditional convergence. It's either going to converge absolutely or it's not going to converge at all. Okay, so looking at number 1, this series does have negative terms and it is an alternating series. And right off the bat, I can say that this series does converge by the alternating series test. So we know that this series converges by the alternating series test. And for the intent of this video, I'm not going to go into the details of why this converges by AST, but hopefully you see the limit of this a sub n is equal to 0 and the terms do decrease in absolute value. So a common test that we will often use when we are determining absolute convergence is the ratio test. And the reason why the ratio test is so helpful is because since we're looking at absolute value and the ratio test already uses the absolute value of the ratio of terms, it's a natural fit. So I might say something like, let's look at the limit Okay, and actually before I do the ratio test, I apologize. Before I do the ratio test, I should probably make sure I know what the absolute value of this series looks like. So the absolute value of my original series would look like the following. Well, what is the absolute value of my alternator, -1 to the n? Well, that would just be 1. And the absolute value of this factorial is just n factorial. So the absolute value of the series looks like this. So now that I know what the absolute value of my series looks like, now let's applying the ratio test. We're going to say 1 over n plus 1 factorial, the next term, divided by our current term. And I'm going to write this for a second, but I'm going to clean it up because I know that when I divide by a fraction, it's equivalent to multiplying by its reciprocal. So I'm going to go ahead and erase this and just write this as n factorial. Okay, just some quick algebraic manipulation there just to clean things up a little bit. All right, so I'm applying the ratio test right now. I'm dividing the next term by the current term. Well, if I can simplify that, because I know how to simplify my factorials, my n factorials are going to divide out, so all I'm left with is 1 over n plus 1. And what is the limit of this ratio? That's equal to 0, which is less than 1, which means by the ratio test, by RT, this absolute value of the series converges. And if you know the series converges absolutely, right? Or excuse me, if you know the absolute value of the series converges, this original series, we can say, therefore, this original series, -1 to the n, converges absolutely. So we've shown that the absolute value of the series converges, therefore, this original series converges. So we can write the following here, okay? Now, quick thing. So since we showed that the series converged absolutely, did we have to even show that it converged in its original state? And the answer is no, we don't need to, right? Again, if it converges absolutely, we know it converges in its original state. But sometimes if we do the absolute value and that series of the absolute value actually diverges, then you have to check to see if the original series does indeed converge, in which case it would converge conditionally. Or maybe the original series doesn't converge at all. All right, let's try this next one, number 2. Again, at first glance, hopefully we see that this series converges by AST just right away. This series does converge by AST. But now I'm concerned with looking at the absolute value of this series, which would look like the following. So the absolute value of the series, if I take the absolute value of the alternator in the numerator, I've got 1 over root n plus 1. Now, what do we know about this series? What test might we use to check the convergence of the absolute value of this series now? Well, I think I'm going to use a comparison test because I feel like I can compare this pretty easily to the following series. And you know what? I apologize, there is a typo in here. I want my lower index to be 1 so I can use this comparison test. Should have done that from the beginning. So apologies. All right, so what would be a good helper series to compare this to? 1 over root n. And what do we know about this helper series? We know that this series here, this series diverges by the p-series test because my p-value is equal to 1/2, which is less than 1. So the absolute value of my series does, my helper series does diverge. Now, what does that mean about my absolute value of my series? Well, can I do the direct comparison test? Well, no, I can't because the denominator of my absolute value series here, this denominator is actually larger. Therefore, this series is smaller than my helper series. And just because your larger helper series diverges doesn't mean that you yourself are going to diverge. But that's okay because we can just quickly do the limit comparison test. So as n approaches infinity, now I'm going to divide this series by this series. So again, hopefully you know how to divide fractions, but I'm just going to go ahead and jump to being able to write this as root n over root n plus 1. Well, what's the limit of that? This is equal to 1, which is both positive and finite. Therefore, this series also converges, or excuse me, also diverges, I apologize, also diverges by the limit comparison test. So since we've determined that the absolute value of our series also diverges by the limit comparison test, Therefore, my original series that I was trying to determine the convergence for, turns out this is what? If it converges in its original state, but it diverges in its absolute state, we say this one converges conditionally. Again, had I been just simply asking you, hey, does this series converge? You could have been able to stop there with the appropriate justification. But hopefully this helps see what you would need to do if you wanted to see if this was conditionally or absolutely convergent. And the final one over here that I want to discuss is number 3. This should take you just a few seconds at this point. I know we might be a little confused now since we've been talking a little bit about absolute versus conditional convergence, but bottom line, what do we notice about this series? A sub n. Well, n plus 3 over n plus 5. What do we know about this series? The limit of a sub n is equal to 1, which is not equal to 0. Therefore, this series diverges by NTT. And I know that there might be some confusion. You might be thinking, well, wait, hold on. Didn't you just take the limit of the absolute value of this series? Yes, that is true. Well, doesn't that mean it could still conditionally converge? And the answer is no, because of the reason we know the series diverges. It diverges because the limit of a sub n is not equal to 0. And no matter what, go all the way back to our NTT lesson. If the limit of your a sub n is not equal to 0, then you know this series cannot converge. It must diverge. So I encourage you now to try the next couple of problems. I've uploaded my solutions to Classroom, so you can go ahead and check there. And hopefully this helps understand absolute convergence.